problems one by one. So the first question is, we have a simply supported beam subjected to a load W. Let this be A, let this be B, let the total length be L. Now here, as you can see, first thing we need to do is we need to check what is the number of possible plastic hinges. So first thing is the number of possible plastic hinges. So before we do that, let us say the first thing, let us say we have to find out the degree of static indeterminacy, Ns. The degree of the simply supported beam is statically determinate, therefore degree of static indeterminacy is 0. Second thing we need to find out is the number of possible plastic hinges. Here if you look, there are no interior support. The only thing we have is we have a concentrated load. So below the concentrated load we will have a possible plastic hinge formation. So the number of possible plastic hinges, that is represented by N, that is equal to 1. Third thing is we need to find the number of plastic hinges required to form a mechanism, that is nothing but Ns plus 1. So we have 0 plus 1 equals 1. So one plastic hinge is formed, then the mechanism will be formed. And the fourth thing is the number of mechanisms that are possible. So the number of mechanisms can be found out as we know, it is N minus Ns. So that is also 1. So only one mechanism is possible, and if one plastic hinge is formed, that mechanism will be formed, and that mechanism will be formed under this particular load. So let us see how to solve it further. So these are the preliminary steps that we have to take. Next thing is, so this is the given beam and this is the load W. The plastic hinge is going to be formed right below the load. So let this be the plastic hinge. So the deformed shape of the structure will be like this once the plastic hinge is formed. Now this is A, this is B. If we consider this particular angle as theta, then this vertical distance will be A into theta, and this angle will be also theta, alternate angles, interior alternate angles. Now if this distance is A theta, then this angle will be A theta divided by B. So this angle will be A theta divided by B. If this angle is A theta divided by B, then this angle also will be A theta divided by B. So now what we have done is the geometry of the entire is being done. Let MP be the plastic moment capacity. Okay, let MP be the plastic moment capacity. Now what we have to do is we have to apply the principle of virtual work, that is the internal virtual work done is equal to the external virtual work done. Okay, so the internal virtual work done will be done by the plastic hinges, this will be done by the plastic hinges, and this will be done by the external loads. So the work done by the plastic hinges will be MP multiplied by initially the member was straight like this and now it has rotated like this. So the total change in angle is one theta is here and another theta is A divided B into theta. So the total change in angle is theta plus A divided by B into theta. This is the total internal virtual work done. This is equal to external virtual work, nothing but force into the displacement, that is W multiplied by A into theta. Now if we simplify this, mp into theta into, it is going to be a plus b divided by b, that is L divided by b is equal to W a into theta. What we are going to get is mp is equal to W ab divided by L, or in other words the collapse load WC is equal to MPL divided by AB. So this is the collapse load. Now as a special case, what we can do is we can see what will be the collapse load in case the beam is having central concentrated loading. So this is becomes L by 2, this becomes L by 2. So in this particular equation, if we substitute A and B as L by 2, what we are going to get is, we are going to get it as 4 MP divided by L. So this will be the collapse load in case of a simply supported beam with central concentrated loading. Now let us try another problem. The second question that we are going to consider is that of a propped cantilever. So what we have is a propped cantilever, and let us say we have a central concentrated load W. Let this be L by 2, this becomes L by 2. Again, the different terms that we have to find is, first one is the degree of static indeterminacy, that is 1. Second thing is the number of possible plastic hinges. Now how do we find the number of possible plastic hinges? That is, we have to look into the different locations where the plastic hinges can be formed. So fixed support, fixed support is a point where we can have plastic hinges. So fixed support, again I forgot to mention fixed support. Fixed support is nothing but a point where fixed support as well as interior support, they are points where hogging moments can develop or negative moments can be maximum. Therefore they are points of possible plastic hinges. So we have one fixed support here, so one point is there. Second one is in the span, if you look, we have a concentrated load, therefore below the concentrated load also a plastic hinge can form. So the total possible plastic hinge locations are 2. Next thing is, what we have to find is, we need to find the number of plastic hinges that are required to form a mechanism. So the number of plastic hinges that are required to form a mechanism is ns plus 1. So if you go for ns plus 1, we will be getting it as 2. So if 2 plastic hinges are formed, then the mechanism will be formed. And the last thing is, we need to find the number of mechanisms that are possible. So the number of mechanisms that are possible is going to be nothing but the number of possible plastic hinges minus ns. So if we go for 2 minus 1, we will get it as 1. So only one mechanism is possible, and to form that mechanism we require 2 plastic hinges to be formed. Let us try to see that mechanism. So the mechanism is going to be like this. One plastic hinge is going to be formed at the fixed end, because the fixed end is a point where there can be maximum hogging moment, and another plastic hinge is going to be formed at the under the concentrated load, because that is a point where the span moment can be maximum. Now this will be the deformed shape of the beam. Now at the plastic hinges we will have the moment as the plastic moment capacity MB. So those will be the moments. Now if this is going to be, since the load is applied at the center, the deformed shape is going to be symmetric. So if this angle is theta, then this particular distance is going to be L by 2 into theta. This is W. And if this is L by 2 into theta, this angle also will be theta. Now if you look here, this angle is theta, this angle is also theta. So now the geometry of the mechanism is complete. Having completed the geometry of the mechanism, now we can proceed to the virtual work equation. So the internal virtual work that is done by the plastic hinges is equal to the external virtual work done, and that external virtual work is done by the external loads. So if we equate them, what we are going to get is internal virtual work done by the plastic hinges. So first plastic hinge, the change in angle is theta, so mb into theta, plus for the second plastic hinge, the total change rotation that has occurred at the plastic hinges, theta plus theta. This is equal to the work done by the external load, that is W into distance, that is L by 2 theta. So what we are going to get is 3 mb theta is equal to W L by 2 theta. So WC is equal to 6 mb divided by L. So this is the plastic moment capacity for a propped cantilever with central concentrated loading. Now let us consider another question. So this time we are going to take up a fixed beam subjected to a UDL W, which is in kilonewton per meter. Here again, first thing is we need to find the possible plastic hinges, number of possible plastic hinges. There are two fixed supports, therefore there are 2 points of maximum hogging moment. So 2 points are coming from the supports. Another is there can be a point where the span moment can be maximum, and because of symmetry it will be the center point. Therefore one more point is there. So there are total 3 points of possible plastic hinge location. Next thing we have to do is we need to know the degree of indeterminacy. As you know, the degree of indeterminacy is 2 here. Next thing is we need to find the number of plastic hinges that are required to form a mechanism, that is ns plus 1, that becomes 3. And last thing is we need to find the number of possible mechanisms, and the number of possible mechanism is nothing but n minus ns, and in this case it is 3 minus 2 equals 1. So only one mechanism will be formed, and to form that mechanism we require 3 plastic hinges to be formed. So let these be the 3 plastic hinges. So these are the 3 plastic hinges that can be formed. They are formed at the supports because they are points of maximum hogging moment, and they are formed at the center because that is a point of maximum span moment. So this will be the deformed shape of the structure, or we can call it as the mechanism. And there is of course the loading acting on it. Now since this angle is theta, this would be L by 2 into theta, and this would be theta, and this would be theta and theta again. And each of these plastic hinge will have mb as the plastic moment capacity. Now once the mechanism has been, geometry of the mechanism is completed, we can write the virtual work equation, that is internal virtual work done by the plastic hinges will be equal to the external virtual work done by the loads. So for the plastic hinge it is mb into theta, for the second plastic hinge it is mb into theta plus theta, and for the third plastic hinge it will be mp into theta. And in case of the work done, the total load is W into L, this is the total load, into average distance. The average distance will be half of L by 2 theta. So we will be taking half of L by 2 theta as the average distance. The total distance is L by 2 theta, so average of that will be half of L by 2 theta. So now what we are having is 4 mb theta is equal to, this will be W L square by 4 theta. So if we replace WC, which is a collapse load, that will be equal to 16 mb divided by L square. So this will be the collapse load for the fixed beam subjected to UDL. So this will be the collapse load for a fixed beam subjected to UDL. Now let us consider another case wherein we have a probed cantilever. So this you can do it as a homework. We have a probed cantilever, and for the probed cantilever we are having a UDL. So for a probed cantilever with UDL, W, and this is L. So again, this can be a homework for you. You have to find out the collapse load for this. Now how do we do this? First thing we have to do is we need to find out what is the reaction of this probed cantilever. Now that is a standard relation. You can get it from any of the textbooks or you can by heart it. So that reaction has to be found out. Now once the reaction of at the probe is found out, the probed cantilever becomes statically determinate. Then what you can do is you can write expression for the moment. So or expression for the shear can be found out. So once the expression for the moment or the shear can be found out, the point of maximum moment is nothing but, so if you're finding out mx, what you if you're writing the expression for mx, to find where the bending moment is maximum, you put dmx by dx equal to 0 and you can find the x. Or another way is you can at the point of maximum bending moment shear force will be 0, so you can find vx, expression for vx, and equate that to 0. Either way you can find the location for maximum bending moment, and that location for maximum bending moment in case of a probed cantilever will be, it is going to be located at 0.414 L from the probe. So 0.414 L from the probe will be the point of maximum bending moment. So once you know the point of maximum bending moment, things becomes very easy. The only 2 points the plastic hinge can form. One is at the fixed support because it is a point where the maximum Hogium moment occurs, and second one is at this location 0.414 L because that is the point where the maximum span moment occurs. So once we know this distance is 0.414 L. Similarly, we can get the remaining distance, that is going to be 1 minus 0.414 the whole into L. And once you know that, you can find out this geometry also can be worked out, and then the plastic hinge theorem can be applied, and once the plastic hinge theorem can be applied, we can find out the collapse load. So the collapse load for a probed cantilever with UDL in it, the value is going to be WCU will be equal to 11.655 MB by L square. So this will be the value of the the collapse load. So this you can do it as a homework. Now let us try to do another problem. Now in this particular question we have, there is W here and there is 1.25 W here. This is 0.2 L and this is 0.25 L, and the remaining will be, this will be 0.55 L. So this is a particular question and we need to find out again the collapse load for this particular problem. Let us see how to find this out. First thing is, again we have to find out the number of possible plastic hinges. The number of possible plastic hinges is n is equal to, there are 2 points of maximum support moments, so that 2 will be there. Second is there are 2 points of maximum span moments, that is under the concentrated loads. So there are, the number of possible plastic hinges is 4. So 2 support moments and 2 span moments maximum, so it is going to be 4. The degree of indeterminacy, as you know, is 2. The number of possible plastic hinges to form a mechanism is ns plus 1, that is 3, and the number of possible mechanisms is n minus ns, that is 4 minus 2 equal to 2. So there are 2 possible plastic hinge mechanisms, and for each of them there can be 3 for each mechanism to be formed, a minimum of 3 hinges has to be formed. So let us try to see the first mechanism. So let us say mechanism 1. So the mechanism 1 will be like this. Let us say the plastic hinge is formed at both the support moments, and the third plastic hinge, let us say, is formed below the load 1.25 W. So this is going to be mechanism number 1. Now if you take this value as theta, then this would be 0.2 L into theta, and if this is 0.2 L into theta, then we are going to have theta divided by 4 here, that is the remaining is 0.8 L. So 0.2 L theta divided by 0.8 L is going to be theta divided by 4 here. So theta divided by 4 is going to come here, that is 0.25 theta. So this angle again, if this is theta, this would be theta, and if this is 0.25 theta, this also would be 0.25 theta. So now the geometry has been completed. Here the load is 1.25 W. We also need to find out what is the deflection below this particular load. So this distance is 0.25 L and this is 0.25 theta. So 0.25 into 0.25, that is going to be 0.0625 L theta. So this is going to be 0.0625 L theta. So now we have got all the dimensions and the geometry of the mechanism number 1 completed. Let us try to apply the virtual work equation. So the internal virtual work done is equal to the external virtual work done by the loads. So at all the plastic hinges the moment is MP. So the external virtual work done, internal virtual work done is MP into theta plus MP into theta plus 0.25 theta plus MP into 0.25 theta. This is equal to the work done by the external loads, that is 1.25 W multiplied by 0.12 theta plus W into 0.0625 L theta. So if we try to simplify this, what we are going to get is if we try to simplify this, we are going to get WC is equal to 8 MP divided by L. So this is the first value of the value of the collapse load we are going to get from mechanism number 1. Now let us try mechanism number 2. So in mechanism number 2, let us assume fixed hinges again to be formed at the plastic hinges again to be formed at the fixed ends. However, the third hinge that is required to form a plastic hinge mechanism, let us assume it going to form under load W. So if we assume this as theta, this distance will be 0.25 L theta, and if this is 0.25 L theta, this is going to be theta divided by 3, and if this is theta divided by 3, this angle also will be theta divided by 3, and this particular distance is going to be 0.2 L theta divided by 3. The load here is 1.25 W and the load here is W. So this will be the plastic hinge mechanism for mechanism number 2. Now what we have to do is apply the virtual work equation, that is internal virtual work done is equal to external virtual work done. So if we equate them, the internal virtual work done is theta divided by 3 into mb plus theta by 3 plus theta into mb plus theta into mb. So that is virtual work done by each of the plastic hinges. This is equal to 1.25 w into 0.2 L theta divided by 3 plus W into 0.25 L theta. So if we try to simplify this, what we are going to get is WC L theta divided by 3 is equal to 8 by 3 MP. So further, if we try to simplify, we are going to get WC as 8 MB divided by L. So from mechanism 2 also we are going to get it as 8 MB divided by L. So comparing the collapse load from mechanism number 1 and mechanism number 2, we see that the collapse load for each of the mechanism is the same. So when the collapse load for each of the mechanism is the same, it means that the collapse through each of the mechanism are going to occur simultaneously. So both the mechanisms are going to occur simultaneously, and WC equals 8 MB by L is the collapse load of the structure. Okay, I hope the idea is clear to you. WC equals 8 MB by L becomes the collapse load of this entire structure. Okay, WC is equal to 8 MP divided by L will be chosen as the collapse load of this particular structure. And the last problem that we will discuss in this lecture is so this is L by 2, this is also L by 2. However, one half is having 2 MB as the capacity and the other half is having MP as the capacity, and the load W, let us say, is acting at L by 3. So this is the problem, and what we have to do is we need to again find out the collapse load. Again, the first step is to find the number of possible plastic hinges. So if you look at the support moments, there are two fixed ends, so there are 2 points of maximum hogging moments, so 2 from the support. If you look into the span, there is one concentrated load, that is 1 point of maximum span moment. And another thing, if you look, there is a point of sudden cross section change, so that is another possible plastic hinges. So there are total 4 possible plastic hinges. Degree of static indeterminacy is 2, and the number of plastic hinges that are required to form a mechanism is, as you know, is ns plus 1, so that is 2 plus 1 equal to 3. And the number of plastic hinges, number of possible mechanism is n minus ns, that is 4 minus 2 equal to 2. There are 2 possible plastic hinge mechanisms. So let us consider mechanism number 1. So if we consider mechanism number 1, what we are going to do is we are going to assume that plastic hinge are obviously forming at the supports. In addition to that, let us assume the plastic hinge to form under the load. So if this is theta, this will be L by 3 into theta, and this angle will be theta. If this is L by 3 into theta, then the angle that we are going to have here will be theta divided by 2. So this angle will be theta by 2, and if that is theta by 2, this also will be theta by 2. Okay, because this distance is L by 3, this is 2L by 3. Basic geometry. And this is W. Now another thing we have to look is the plastic moment capacities. The plastic moment capacity here is 2 MB. At this particular point below the load also the plastic moment capacity is 2 MB, and at this point the plastic moment capacity is only MB. So this completes the geometry of the mechanism. Now we can apply the virtual work equation, that is the internal virtual work done is equal to the external virtual work done. So that is 2 MP into theta plus 2 MP into theta plus 0.5 theta plus MP into 0.5 theta. This is equal to W into L by 3 theta. So if we try to simplify this, what we are going to get is, we are going to get WC is equal to 16.5 MB divided by L. So this is the collapse load as per mechanism number 1. Next is, let us try mechanism number 2. So for mechanism number 2, we are going to assume plastic hinges to form at both the ends and at the point of sudden cross section change. So this is the plastic hinge, this becomes L by 2, this becomes L by 2. If this angle is theta, this becomes L by 2 theta and this becomes theta. Again we have the load acting here, that is W. This distance is L by 3, therefore this distance moved by the load will be L by 3 into theta. Now another thing we have to remember is the plastic moment capacity here is 2 MP. This particular point that we have here, it is a junction of 2 MP and MP. We will choose the lower value as the capacity. So when you have a junction of two plastic moment capacities, choose the lower value as the capacity. And here we have MP. And if we look here, this is theta and this is theta. Again, the geometry of the mechanism is complete. Internal virtual work done should be equal to the external virtual work done. So the internal virtual work done is 2 MP into theta plus MP into theta plus theta is plus MP into theta is equal to W into L by 3 theta. Now if we try to simplify this, what we are going to get is 2 plus 2 is 4, 4 plus 1 is 5. What we are going to get is, we are going to get WC as 15 MP divided by L. So this is the collapse load as per mechanism number 2. So if we consider both the mechanism, the collapse load as per mechanism number 2 is the smaller collapse load, and therefore we have to choose the smaller value as the collapse load of the entire structure. So collapse load of structure is equal to the smaller of the various mechanisms considered. So that will be equal to 15 MP divided by L. The other one was 16.5, which is higher than this value. So this becomes the collapse load of the structure. Okay, so I hope the idea is clear to you. In the next lecture, what we will be doing is, we will be dealing with the plastic analysis of continuous beams. So whatever we learned in this lecture will be applied for the plastic analysis of continuous beams. We will stop for this particular lecture. Thank you.